Hello everyone, my name is Anup Das and I am an assistant professor at Drexel University. Welcome to my talk on DATACON, an architectural technique on improving phase change memory performance via data content aware accesses. This work is a collaborative work between Drexel University and ETH Zurich. The work is performed by my doctoral student Shihao Song. The other co-authors of this paper are Professor Onur Mutlu from ETH Zurich and Professor Nagarajan Kandasamy from Drexel University. I will start with an executive summary of this work. We made two key observations in this paper. First, during PCM write, latency and energy are sensitive to the data to be written and the content that is overwritten. The overwritten content is unknown at the time of write. Our second observation is that overwriting all zeros or all ones content incurs lower latency and energy because the PCM cells are programmed in one direction only, that is, using set or reset operations, not both. These two observations lead to our idea of data content aware PCM writes, which overwrite unknown content only when necessary, otherwise improve latency and energy by overwriting all zeros and all ones content. DATACON is based on two key mechanisms. First, address translation, that is to translate logical address to physical address, which contains the all zeros and all ones content. Second, reinitialization, where we methodically reinitialize unused memory locations with all zeros and all ones. We do such reinitializations in a manner that does not interfere with regular read and write accesses. We evaluate DATACON with SPEC CPU 2017, NAS parallel, and TensorFlow benchmarks. We show that DATACON results in 27% performance improvement and 43% energy reduction. To start with, we give a brief overview of PCM or phase change memory, which is a non-volatile memory where data is stored as resistance of cells. The figure to the left shows the structure of a PCM cell built with chalcogenide material and a heating element to induce phase changes. The figure to the right shows the temperature profiles needed to read, set, and reset in the cell. The reset operation is a transition from the crystalline state or logic 1 to the amorphous state or logic 0. The reset operation is fast but requires higher energy. The set operation is the transition from the amorphous phase or logic 0 to the crystalline phase or logic 1. The set operation is slower but requires less energy than reset. In this slide, we demonstrate the PCM write operation in a baseline system using the program and verify method. The first figure shows the write data and the overwritten content. In the second figure, the two content are compared to identify the bit positions that need to be set. This is then programmed in the write driver. In the third figure, the write driver generates set current to program the selected cell, which is shown in green. In the fourth figure, the write data is compared again with the overwritten content to identify the bit positions that now need to be reset. Finally, in the last figure, the write driver is programmed to generate reset currents to program the selected cells shown in green. As can be seen, at the end of the programming, the final content becomes equal to the write data. And we say that the memory location is overwritten with the write data. The program and verify method therefore uses 4 steps: compare, set, compare, reset for PCM write. In this example, we illustrate two alternative approaches to PCM write. Preset, where the initial content is all ones, and pre-reset, where the initial content is all zeros. In preset, which is shown to the left, only 2 steps are needed for every PCM write: compare and reset. In pre-reset, which is shown to the right, to overwrite the content, only 2 operations are needed: compare and set. As we see, in both preset and pre-reset, only 2 steps are needed for PCM write, whereas if you recollect from the previous slide, in baseline PCM, you need 4 steps. Preset or pre-reset has latency and energy benefit. However, the choice between preset or pre-reset is decided at design time and used for all PCM writes, which is not optimal, as we show in this paper. We make 2 key observations in this paper regarding PCM writes. Our first observation is that the energy benefit of preset or pre-reset depends on the fraction of set bits in the write data. In this figure, we report the PCM energy for preset and pre-reset as a fraction of the set bits is increased from 0% to 100%. Set bits of 0% means that the write data is all zeros, whereas set bits of 100% means that the write data is all ones. The observation leads to our idea. Use pre-reset when the fraction of set bits is less than 60%. On the other hand, use preset when the number of set bits is more than 60%. Our second observation is that the fraction of set bits is workload dependent. The figure reports the distribution of PCM writes with more than 60% and less than 60% set bits in the write data for all the evaluated workloads. The observation leads to our idea that we reinitialize unused memory locations with all zeros and all ones based on the PCM writes in a workload. This brings us to the key idea of DATACON. That is, to serve PCM write, DATACON overrides all zeros and all ones content to improve performance and energy. DATACON overrides unknown content when there are no uninitialized location available in PCM. DATACON implements three components. First, DATACON analyzes the fraction of set bits in the write data. Second, DATACON translates the logical write address to the physical address that contains the overwritten content and record this translation in a table. Third, DATACON methodically reinitializes unused memory locations with all zeros and all ones content to use them in serving future writes. This brings us to the outline of today's talk. We will discuss detailed design of DATACON, followed by the three components: the address translation, content selection, and reinitialization. We will then present our evaluation and then the conclusion. This slide shows our overall system overview. We consider a hybrid memory where embedded DRAM or EDRAM is used as cache to the PCM-based main memory. We show an example where a 1 kilobyte EDRAM cache line maps to 8 banks in a PCM RAM. We now present the detailed design of DATACON. DATACON introduces 4 components to the baseline design, which are shown in red in the figure. The first is the address translation table, which is used to record logical to physical address translation. The second is the lookup table, or LUT, which caches frequently used address translations inside the memory controller. The third is the address status unit to select the all zeros and all ones initialized content. And fourth is the initialization queue to record unused memory locations that can be initialized methodically. We start with the address translation using a simple example. We first considered a read request, which requests to read the content in address 0x30A. The physical address corresponding to this logical address is first obtained from the lookup table. In this example, the physical address is 11FE. The read request is redirected to the physical address 11FE in PCM, as you can see in this. Now we show an example of address translation of a write request. In this example, we consider the write request is to overwrite address 1078 with the data 5. First, the write data is analyzed to see whether overwriting all zeros or all ones lead to lower energy and latency. Without loss of generality, we assume that the content selector decides that overwriting all zeros is beneficial. The status unit has 2 queues, the reset queue that contains addresses that are initialized to all zeros, and set queue that contains addresses that are initialized to all ones. In this example, an address 910B from the reset queue is used as a physical address for the write address 1078. The new write address is therefore to overwrite all zeros content in address 910B with the write data. Accordingly, the address translation of logical address 1078 to physical address 910B is recorded in the LUT, as you can see in the slide. The unused location 1078 is inserted in the init queue so that the address can be reinitialized methodically by DATACON. Next, we discuss how to select the overwritten content. This slide shows the algorithm for overwritten content selection. The algorithm proceeds as follows. The algorithm first checks if the fraction of set bits in the right data is more than 60%. If so, we are in the right side of the flowchart. Next, we check if there are all ones content available. If so, we select all ones content because overwriting all ones is better for both latency and energy. If there are no all ones content available, the algorithm selects all zeros constant instead. This is to prioritize performance. Finally, if there are no all zeros or all ones content available, the algorithm selects unknown content. These steps are detailed in the paper. A key takeaway from this algorithm is that DATACON overrides unknown content only when there is no all zeros or all ones initialized content available in PCM. Next, we discuss the last component of DATACON, that is the reinitialization. DATACON uses two queues, the set queue and the reset queue, to store the memory addresses with all zeros and all ones content respectively. DATACON uses thresholding to trigger reinitialization requests. These requests are stored in the init queue. However, reinitialization requests are not serviced immediately. A reinitialization request is serviced when both read and write queue are empty, or when the write queue is empty and the reinitialization request is to a partition which is different from the partition of the read request. In this way, reinitialization request can be serviced in parallel to a read request, exploiting PCM's partition level parallelism, which is our earlier work in cases 2019. Now we present our evaluation. DATACON is evaluated on a x86 multi-core simulator whose front end is based on the PIN tool. The simulator integrates cycle accurate memory simulator, the RAMulator for DRAM, and NVMen for PCM. This table highlights the key simulation parameters, which includes 8 cores per socket, private 32 kilobyte L1 cache per core, private 512 kilobyte L2 cache per core, shared 8 megabyte L3 cache, and shared 64 megabyte EDRAM. As for the PCM configuration, we consider a 128 gigabyte PCM with 4 channels, 4 ranks per channel, 8 banks per rank, 8 partitions per bank, and 128 tiles per partition. We use the DDR4 memory interface with a memory clock of 1066 MHz. This slide shows the PCM timing parameters that we use. The read latency of DATACON is similar to baseline PCM, which is 56.25 nanoseconds. By using all zeros and all ones overwritten content, the DATACON write latency is significantly lower than the write latency in baseline PCM. As in this table, you can see that when overwriting all zeros, the write latency is 169.75 nanosecond, whereas when overwriting all ones, the write latency is only 59.75 nanoseconds. This is significantly lower as compared to the baseline write latency, which is 209.75 nanoseconds. DATACON uses the baseline write latency only to overwrite unknown content. We evaluated 3 systems. The baseline systems always overwrites unknown content. This is based on the work by Benjamin Lee at ISCA 2009. The preset technique, which we discussed earlier, is by Moinuddin Qureshi at ISCA 2012. Finally, the flip and write technique of Micro 2009, which uses read request to first read the overwritten content. Then, by comparing the overwritten content with the write data, flip and write programs only the bits that are different. We evaluate DATACON using the SPEC CPU 2017, NAS parallel, and TensorFlow workloads. The figure shows the EDRAM misses per kilo instructions, MPKI, of these workloads. We first present our result on system performance. We plot the execution time normalized to baseline for each evaluated workloads. We observe that the average execution time of DATACON is 40% lower than baseline, 47% lower than flip and write, and 27% lower than preset. Next, we evaluate the memory system energy. The energy consumption is also normalized to baseline. We observe that the system energy consumption of DATACON is 27% lower than baseline, 26% lower than flip and write, and 43% lower than preset. To understand the significant performance and energy improvement of DATACON, we analyze the overwritten content in DATACON versus preset. We plot the fraction of PCM writes in DATACON distributed into writes that overwrite all zeros, all ones content, and unknown content. For comparison, we show the fraction of PCM writes in preset distributed into writes that overwrites all ones and unknown content. We see that DATACON overwrites unknown content for only 4% of PCM writes, whereas preset overwrites unknown content for 59% of PCM writes. By overwriting unknown content for fewer PCM writes, DATACON significantly improves performance and energy consumption. Next, we show the total energy consumption of DATACON distributed into energy to read, write, and reinitialize content in DATACON. We observe that the reinitialization energy constitute only 11% of the total energy consumption. And this low energy overhead of reinitialization is because of our policy to trigger reinitializations based on thresholding. This brings us to the conclusion. We made two observations in this paper. First, during PCM write, latency and energy are sensitive to the data to be written and the content that is overwritten. The overwritten content, however, is unknown at the time of write. Our second observation is that overwriting all zeros or all ones content incurs lower latency and energy because the PCM cells are programmed in one direction only using set or reset operations, not both. These two operations lead to our idea of data content aware PCM writes, which overwrite unknown content only when necessary, otherwise improve latency and energy by overwriting all zeros and all ones content all the time. DATACON is based on two key mechanisms. First, address translation, that is to translate logical address to physical address, which contains the all zeros and all ones content. And second, reinitialization, where we methodically reinitialize unused memory locations with all zeros and all ones. We do such reinitialization in a manner that does not interfere with regular read and write accesses. We evaluate DATACON with SPEC CPU 2017, NAS parallel benchmarks, and TensorFlow benchmarks. We show that DATACON results in 27% performance improvement and 43% energy reduction. Thank you for your attention. If you have any questions, please feel free to reach out to my student Shihao, whose email address can be seen on this slide.